Okay, so are there any questions before we move further? Okay, so let's see what is going to be the output of this code, right? So what is your suggestion? Unknown variable from the GPU side is what Shikhar says. Okay. So what is the reason, Shikhar?
Sir, because this message, basically this string table is created with the CPU to hold hello world string.
Right.
The GPU doesn't know the existence of such string table.
Correct. So this message is a CPU variable, right? It's a global memory, but global memory of the CPU, the way we understand from C programs, and therefore that is not going to be accessible from the GPU, which is this code, and therefore even at compile time itself you will get an error. Okay, so our takeaway is that CPU and GPU memories are separate, and there exist uh, GPUs called integrated GPUs where the CPU and GPU memories might be shared, but by and large we are going to look at the server end GPUs where the GPUs are separate. In contrast, if you do a hash define, then that should be okay because it's just a string replace. Right? It's not a separate variable. All right, so this is the diagram that we were trying to draw a couple of slides back. So this is a CPU, a GPU, right? They are connected by a bus. They have their own separate memories. And since these memories are separate, we need to copy the memory across CPU and GPU. And that means that as we were discussing, that the amount of memory that you require is going to get doubled, right? Once on the CPU and on the GPU. Yes, that is going to be the case. So we have to maintain these copies of variables, and in addition, it is our responsibility as a programmer to ensure that they are in sync. That is, since these are now copies, it's possible that they might go out of sync with each other. Some CPU memory might be more recent, whereas GPU memory might be an older value, right? So we have to ensure that it is in sync. Yeah, go ahead, Sandeep. Oh, Sandeep is saying when I tried with constant n equal to 10, it worked. That should be okay, right? So n is a variable which you can pass as a parameter. So even if you don't try constant n, oh, you're saying that it directly worked on here, is it? My guess is that it is the compiler is converting that, since it's a constant, it is converting it into a mnemonic 10. You might want to, yeah, so n, it's not directly accessing n, it's accessing 10 on the CPU, and that's the on the GPU, and therefore it is working, right, as a constant value, not as a variable. Right? So my feeling is that the compiler is doing its trick. Um, so Shyam Murthy says the only interface for the CPU and GPU through the shared memory. In other words, there is no other connection like network interface, etc. for the GPU. Is this correct? Yes. Currently, I mean, in the context of our discussion, yes, there is no direct interface between CPU and GPU except for this PCI Express bus. But there are technologies currently where you might be able to access CPU disk directly from the GPU, right? So that requires specialized hardware which will have additional connections. So that is provided in some context, but by and large, the GPUs that you will be accessing are likely to have only this PCI Express bus as the interconnect.
Hello, sir. Am I audible?
Yes, Sandeep, go ahead.
Sir, if we use the macros like hash define n, so while the compilation is happening, n is replaced with that number, right?
That is
so,
correct.
but I checked with my compiler that if you write it as constant int n and try to modify it, the compile error is that the n is the constant, and if you modify the macros, it will say that like 100 is equals to 100, like that is the error. But when it comes to constant int n is not replaced by the 100 during the compilation, I feel. Because if that is the case, the error I should get is 100 is equal to 100, right?
That is correct. You are right. But you are having that statement on the in the GPU kernel or the CPU function.
In the CPU, like I
Yeah.
just tried whether the compiler is replacing the n, this constant in n 100 in the compilation time or not, but it is not happening, I guess, because the error is different.
You are right. That observation ensures that on the CPU, when you have n equal to 100, it's not getting replaced with 100 equal to 100. That is correct. And therefore, it's actually considered as a variable. That is correct. So,
Then
on,
yes, sir. Then why am I not getting error when I'm trying to print that n in GPU, that is in kernel?
so what is possible? I think we'll have to the assembly code to ensure that that is what is happening. With NVC. Default 3 optimization. Uh, can somebody confirm that I'm audible? I'm audible?
Yes, sir. You are audible, but I don't know from my side it is
Yeah,
breaking.
voice is breaking. Yeah.
I
I feel it's
faced a
breaking.
disconnect. I don't know if I'm still audible to you guys. Somebody confirm that, please. Okay, fine. Thanks. Okay, sorry, I am facing some network issue. Uh, I guess the screen is no longer shared, so let me share that. Right. So we were discussing that why is it the case that that n is working on the GPU? Since the GPU code is optimized with O3 flag, it's likely that it is converting it into a constant. That is my guess. Right. We'll have to look into the assembly code to finally confirm it. Whereas the CPU code continues to be O0, which is the default, and therefore it might not do this transformation on the CPU side. That is my guess. Therefore, it might be working.
So what are the flags?
Sorry, I didn't hear that,
Sir, you were
Sandeep.
saying some flags, right? Can you give some clarity? Like what are these flags?
Yeah, so I'll just write it in the chat. -O3. So when we say GCC-O3 file.c, it optimizes with more optimizations, right? So that O3, the default when we say GCC file.c, the default is O0, that it is not going to do many optimizations, just very basic ones. But O3 is going to enable many more optimizations. It's going to take more time for compilation. So that O3 is enabled by default for the GPU code. So that could be one reason why that n might be getting converted, might be getting allowed. Whereas, but I believe that if you write only int n equal to 10, then it should not work. I mean, because we are marking it as a constant, it might be working.
Can you explain this program again? I joined late actually.
This particular program, this
Yeah.
just says that since message is on the CPU, MSG variable, therefore it is not accessible on the GPU, and therefore we will get a compile time.
Okay, so the constant character. Okay, this is
Yeah,
okay. So it will give the some error, is it? Or it
it
will
will
not.
give this kind of error that MSG is inaccessible on the GPU. And
Okay.
what we know this testing further to our discussion is that because it's an array, that is right, it might not be able to do this optimization except for, let's say, primitive values like integer, float, character, etc. That's right. I mean, that is my guess. We'll have to understand it by looking directly at the assembly code. So the
But
GPU, yeah,
there
sorry.
is a,
Sorry.
no way to copy from CPU to GPU because earlier we used to copy from GPU to CPU, but there is a no way to reverse copy, correct?
There is. We will be able to do that. In fact, that will be required in this case. That MSG needs to be copied to the GPU, and then the GPU should make use of it. So we'll do that, and that is going to help us do the copying from device to host, that is GPU to CPU, as well as host to device, which is CPU to GPU. Right? So yeah, so both ways it is possible. Yeah, so Sandeep agrees. Abhishek says without the constant, it is an error. Yeah, thanks Abhishek for checking. Okay, so we were discussing this and we said that keeping the copies in sync is our responsibility as a programmer. Okay, so the typical CUDA program flow happens like this. We have seen already a program, but now we will make it more generic, which will give you a high level idea of this. So we have the CPU and the GPU, and there is some data which you might want to read from the file system. Let's say some parameters or some simulation data that you might require, etc. Or you might generate it on the fly using random function, etc. So that is first step, to populate the data in the CPU memory, okay, in the host memory. The second step is, now when you require that data to be processed, we copy it from CPU to GPU using CUDA memcopy, right? And in CUDA memcopy, we'll use host to device instead of device to host here. So we are copying from host to device. The third step is, of course, to process it on the GPU in parallel, right? That is execute the kernel. The fourth step is to get the results now. The results are now available on the GPU after the kernel processing. So get those results copied from device to host or from GPU to CPU, and then start processing it further on the CPU, typically in a sequential manner, but you can also do parallel programming on the CPU also. That is beyond our current focus. And that further usage of the results might require you to go back to the GPU and launch another kernel, etc. So this cycle might repeat. Okay, so this is a typical program flow which you will have in most of your programs. So the loading data can be done using file reading operations or random number. Data from CPU to GPU is essentially host to device. Calling the GPU kernel, we do something like x comma y, and then getting the results back, we do device to host, that is from GPU to CPU, right? And then using results on the CPU, right? And since we have these two, I mean, copies, therefore we need, you will often see such kind of core CPU array, GPU array, CPU matrix, GPU matrix, CPU graph, GPU graph, etc. As we were discussing, that there will be copies and we will have to keep those in sync. Okay. Okay. If there are any questions so far, please feel free to ask. Okay. While I am showing this code, what you have to do is to understand this code and tell me the output of this. Okay, so you have to understand this code and think about what will be the output of this code. And meanwhile, if there are any questions, I can take those up now. I'll wait for a few more seconds for others to try out. Okay, so as Sandeep and Shomik have rightly pointed out, and Satya Bhagwan has pointed out, it's shifting the characters to the next character, and therefore this is likely to print hello world in some way. Right, so let's understand. I mean, that exact printout is not so much important as understanding this code. Right, so we have a CPU character array which is populated with some values, and then there is a pointer which is similar to our DA from the previous program, which is going to point to a GPU memory. How? Using CUDA malloc. So CUDA malloc allocates some memory size of character into 1 plus string length, which is for the /0, and that is going to be memory being pointed to by GPU array variable. Then we copy from CPU to GPU. That is, this string is copied from host to device. Right? How many bytes is what is specified as the third parameter. Okay. And then we call the kernel with that GPU array as an argument. Right? So since we don't know what is the length of the string, and we want this to be a parallel program, we don't want to keep finding that /0 by every thread. Therefore, we also pass a parameter which tells what is the current size of the string, right? Current length of the string. And then we stop the CPU at this stage, right? Which is and followed by CUDA mem copy, which copies from GPU to CPU. The modified string gets copied from GPU to CPU, which we print on the CPU. As noted here, since there is CUDA mem copy, which also blocks the CPU as well as the GPU, this CUDA device synchronize is unnecessary, but nonetheless, we have just maintained. Now let's understand what this code does. So this kernel gets launched with 32 threads, whereas the number of characters here is going to be smaller than 32. So if you are trying to access ARR of ID, right, which where ARR is the pointer that is being passed, which is the GPU array, then individual thread might be pointing to is going to point to different characters into this array, right? Thread 0, thread 1, thread 2, thread 3. And there are 32 threads, so there might be some thread which is pointing here, which create an array length, incrementing the value, right? Because it's a character, is a massive value. I'm about to increment it. So G becomes D E becomes the network is playing its role. So our CPU GPU connection between us is getting affected. Sorry about that. Yeah, so that /s1f is the ASCII value 31, because 32 is the ASCII value for space, and like that you can see the other values. Okay, so this is going to print hello world, right? And whatever is the ASCII value after hyphen, that is going to get printed, maybe bang or something. Okay, any questions on this code?
Sir,
Yeah, go ahead.
here our CUDA memcopy and the kernel call both are in parallel to the printf. I mean,
No, CUDA memcopy also gets added to the same work queue, and therefore CUDA memcopy happens only after the first CUDA memcopy is over. Then only the kernel is taken for execution, and then only the second CUDA memcopy will be taken for execution after the kernel is fully executed.
but these after the final CUDA memcopy, we have the printf, and this printf is in parallel with the CUDA memcopy.
Oh, I see, I see. No, so that will not happen. So CUDA memcopy is blocking the GPU operations as well as it is blocking for the CPU by default, right? So it is like our usual CPU related function calls which are going to finish and then the next instruction gets executed. So CPU memcopy is not asynchronous on the CPU. So it is synchronous. That means it is going to block the CPU also.
Okay.
Right. Since you asked, there is CUDA memcopy async, which ensures that you initiate the copy and then the CPU moves ahead. Right. In that case, there will be a problem, but in this case, there is.
Okay.
Any other questions here? Okay, so when I get logged out of this, I also lose the chat messages. So in case you had asked a question which I have not answered, you might have to ask that again. Which, yeah. Okay, so we'll move ahead from here. So let's say that you try to write this program, right? So you don't have to write it right now. You can as well write it. But let's say that we write a CUDA program to initialize an array of size 32 to all the zeros in parallel, right? So this code is going to look very similar to our squaring program, where I'm going to launch it with 1,32 as the launch configuration. And then in the kernel, I'm going to use threadidx.x to initialize it to 0, a of threadidx.x equal to 0. Right? So that is how it is going to be. Now I'm asking you to change its size, that array size, to 1024. Okay? So instead of CUDA malloc of 32, I'm going to do CUDA malloc of 1024. I'm going to launch it as 1,1024, and that is likely to work. Right? So as Soumik has also suggested that it will, you require a of thread ID equal to 0. And interestingly, that will work. Okay. Now let's try to change that to 8,000. So I'm going to do CUDA malloc of 8,000 integers. So that will work. But when I try to launch it with 1,8,000, that is not going to work, right, on all your GPUs. And the reason being that there is a limit to that second parameter in the launch configuration, the triple left and triple right arrows. 1,8,000 is not going to work, whereas 1,1024 is going to work, right? So there is a limit, and let's understand now that what that means, right? So I'll leave this as homework exercise.
Sir, one question.
Yeah, go ahead.
Sir, in the kernel, the parameters are available to all the threads, while the variables within the kernel are local to each thread. That is.
Parameters are available to all the threads, that is correct, whereas the variables inside the kernel are local to the threads. You are right.
Okay. Okay.
Let me get back to the presentation. Right. So this requires us to understand how those two parameters work. Right? So the two parameters are best understood using, let's say, some analogy. Right. So let's say that all of us together are going to, let's say, from IIT Chennai, IIT Madras to Mahabalipuram, right, which is nearby. And we all, I mean, it's a large number, maybe 60 people. But then the buses are small. Let's say there are only 10 people can sit in one bus. right? So we require, let's say, 6 buses to go to Mahabalipuram. Now, if I want to identify each person, right, inside the bus there is a seat number, right? So 1 to 10 are the different seats. So I'll be able to identify a person locally within a bus as seat number 1, seat number 2, up to seat number 10. And this is going to be common across all the buses. But if I want a unique ID given to each participant, then I need to take into account the bus number. Okay, so bus number 1, 2, 3, 4, 5, 6. And if I say that a particular bus number B, right, into 10 plus the seat number, right, that is one unique way of identifying a particular participant. Okay, bus number into 10, where 10 is the seating capacity of each bus, and plus the seat number, that is going to give you a unique number, and not only unique number, it's going to be consecutive. Right, so 1 to 10 as the first bus, then 11 to 20 for the second bus, and so on, all the way up to 51 to 60. This is the mechanism which gets used inside CUDA for these two numbers that we specified for the kernel launch. The second parameter is the local seat number, which is thread idx.x. The first parameter is the number of buses. Okay. So there are going to be, when we say 1, 32, there are 32 seats in one bus, and I am going to Mahabalipuram with one bus. When I say 3, 100, each bus contains 100 seats, and there are 3 such buses. Okay. So when I try to access only using the thread idx.x, I am just using the seat number that is not going to be unique across all the buses. If I take into account the bus number also, then I get a unique number. The bus number is decided by something called as a block idx.x. So the bus is mapped to something called as a thread block or only a block, and then the second parameter decides the number of threads per block. So those are the two entities which we are going to use in this particular example, right? So I am going to use 2-dimensional data, which is essentially a matrix, right? But I will specify it as 1-dimensional array of n into m size. So there is a matrix. Let's use this. There is a matrix on the GPU. There is matrix on the CPU or the host. The matrix on the GPU needs to be CUDA malloc as n cross m size, and the matrix on the CPU is only malloc, right? That is on the CPU. Right. So these numbers are arbitrary. You can change those anytime. And I'm going to launch it with n, m, which means that there are n buses, each containing m seats, n thread blocks, each containing m threads. Okay. And I'm passing this matrix as a parameter. This matrix is going to get populated inside the kernel, which we are going to write later. And then the matrix is, after populated, is going to get copied to the host matrix, which I am going to print in a nice tabular manner. Okay. So that tabular manner is happening using the host matrix. So since we are using the single dimensional array, I need to do it with respect to the bus ID and the seat ID, right? Or the row ID and the column ID, right? Multiplied by the number of seats within each bus or number of columns in each row, right? As a matrix, n cross m matrix. So how will the kernel look like, which is going to initialize this data in some way? It could be all zeros, or it could be some unique value being assigned, etc. So we would like to write that, and let's see how it looks like. So the first line is __ global. It's going to return void. Dkernel is the name of the function. It takes unsigned star matrix as a parameter. Okay. We would like to, so this particular kernel is going to get launched with n into m number of threads, right? In this case, 30. And we would like to give unique ID to each thread so that matrix of ID equal to ID is going to initialize this matrix with, let's say, 0, 1, 2, all the way up to 29. Right? 29 is n into m minus 1. This is decided by the block ID and the thread ID. Okay? So thread ID is the local seat number within a thread block, local thread within a thread block, and the block ID is the bus number, and that multiplied by the size of the bus, number of seats in the bus, which we have also specified as m. Right? So the m maps to block dim dot x, which is the dimension of the block, size of the block. Okay? So if I initialize this as 5, 6 or n, m, 6 is going to be block dimension dot x. Block idx dot x is going to range from 0 to n minus 1 or 0 to 4. And thread idx dot x we know is going to get is going to span 0 to m minus 1 or 0 to 5. Okay, and using this multiplication, you are going to get a unique identifier for each thread. Okay, it's going to be consecutive from 0 to 29, and therefore different threads access different values or different memory addresses, and they initialize it with 0 to 29 as the initialization value. This particular formula is likely to be common across many of your programs, right? If you continue to write CUDA programs, and you will realize that this is something which you will kind of by heart, you will learn as you start programming more. Right? So you will find this in almost all the codes which you will encounter in CUDA. Okay, so that gives you a unique ID. Yeah, any questions on this particular part of the code?
Sir, is there a cap on block dimension?
Yeah, so there is a cap on block dimension. In fact, the classwork that I gave, that find out what device query does or where device query is. Device query is a program given by CUDA, which allows you to find out what are the characteristics of your GPU installed on your system. So it will give you, for example, the maximum number of threads you can have on your thread block, which is typically going to be 1024. Similarly, it will give you how many maximum number of thread blocks you can launch inside a kernel, and that is typically a very large value, maybe 2 to the power 31 or something. So practically infinite, but yes, there is some maximum.
What the unsigned? Can you? What the type of that unsigned?
Unsigned is, I mean, integer is signed, which is going to have both negative and positive values. Unsigned is just going to get the 0 onwards positive values.
Okay.
Yeah, so Rishikesh says, is there a limit on number of blocks? Yes, there is a limit, which is going to be very large. So for millions, you are not going to face any problem. If you want to get into billions, then there will be some small, I mean, you will have to check for that limit. Right. So let's
Sir, I wanted to ask a small thing.
Yes, sir.
Yes. So, as you have discussed that inside a thread block, the parallelism is existing, but across multiple thread blocks also does parallelism exist at the interleaved, or there is
Yes.
sequential operation?
Yeah, so that's a good question. The question here is that, is the parallelism within a thread block or across thread blocks? The parallelism exists across both. So within a thread block, there are, let's say, 1024 threads or m threads in this case, which are going to be executed in parallel. In a similar manner, multiple thread blocks might get assigned to different parts of the GPU, and therefore there is parallelism across thread blocks also. That doesn't mean that everything is going to be parallel. It's going to be finally decided by how much hardware we have. That is how many cores we have, plus how they are accessing memory. If that is going to be, if there are free cores, then you will have more threads lined up to be executed. So the maximum parallelism that you can achieve is going to be limited by the number of cores that you have. But yes, across thread blocks also there is parallelism. Any other questions?
Sir, do we have to worry about differences in communication between blocks, threads in specific blocks, or within a specific block amongst the threads? Is there a difference between the communications?
Right. So what Shyam is asking is that when threads want to communicate across them within a thread block or across, is there a difference? Yes, there is a difference, and we'll study that when we come to synchronization. So the reason why threads are organized using thread blocks and then there are is because there is some facility given to all the threads within a thread block. Those two facilities, or primarily two facilities, are one, there is a shared memory available across threads in a thread block within 1024 threads of a thread block. Across, that is not available. If they want to communicate across threads, then that has to go through global memory. The second is that there is some small barrier or fast synchronization available across all the 1024 threads of the thread block. Right, so we'll study that as we go along. But yes, we need to be careful about that when it comes to performance. All right, if there are no further questions, then I am going to move ahead.
Sir, a small question. All these thread blocks can be on the same card or it can be distributed across different cards? I mean, blocks.
Sorry, I didn't understand. So what gets distributed?
The blocks I'm defining, does it has to be on the same card or it can be on different physical cards?
I see. Okay, so let's understand this a little bit. Maybe if I show you the computation hierarchy, it will become clearer in a couple of slides. But nonetheless, I'll mention this. Yes, so multiple thread block. So the GPU has different kinds of hardware. There is cores that we studied, but then cores are also organized into something called as a streaming multiprocessor, or SM. Thread blocks get assigned to these streaming multiprocessors. Okay? And therefore, it's possible that multiple thread blocks might get assigned to one SM. And yeah, so within an SM, if there are enough cores available, then multiple thread blocks might execute in parallel and some might be sequentialized. So does that answer your question, or?
Yeah, I mean, so when I want to engage multiple cards, so what are the exact keywords I'm going to use to? Yeah,
so the mapping of thread blocks to SM is not in our hands at the programmer level. We can decide the number of threads within a thread block. We can decide the amount of memory, but we cannot decide the scheduling of thread blocks to SMs.
Okay. Okay. Thank you, sir.
Okay.
So even multiple kernel thread blocks can be on a single SM, is it?
Multiple thread blocks will get typically assigned to one SM. Typically, the number of thread blocks can be large for real world problems. Number of SMs is going to be limited, maybe 50, 60, 70, like that.
Okay, so, and those thread blocks may be due to different kernels also.
No.
On an SM.
No. It will at a time only one. Okay. So let me put it this way. When we launch a kernel, right, and only one kernel is executing, then all the thread blocks corresponding to that kernel can be spread across different SMs. It's possible to have multiple kernels running simultaneously also. I am not sure if thread blocks from different kernels will be assigned to the same SM at the same time. I don't think that will happen, but it's possible that different SMs can execute codes of different kernels, which means that thread blocks from one kernel will be assigned to one SM, thread blocks from the other kernel might be assigned to another SM. So that is possible. But whether the same SM can get thread blocks from different kernels, that I think will not happen, although I'm not sure. Okay. So we will move ahead. Yeah. So what will be the launch configuration? If I want 2, X in this case, what should I write X to be for the same program to work? Okay, Satya Bhagwan says 15, Science is 15, Pratham's Harshil, Vinoth. Okay, 15. Yes, so that should be m into n by 2, and that leads to 15. Okay, sounds good. That was just a quick check to see if you are in sync. Okay, so the important takeaway is that, so there is a, see, we are talking about this dot x. There is also dot y and dot z, right? So just that we are not going to study that right now. What I'm trying to convey here is that even if you restrict yourself to this dot x, you'll be able to compute almost everything, even two-dimensional data, three-dimensional data also. Right? That dot y, dot z are specified or are supported so that you are able to, I mean, sometimes it becomes easy to map because we are dealing with matrix, this becomes y, this becomes x. But the way we did in the matrix case in this, we were using a single dimensional, I mean the dot x values itself, which was sufficient to cover the whole matrix, right? So even if you learn this, that is going to be sufficient. There are some backup slides using which you can think about dot y and dot z, but in the limited time, I'm not going to go there, right? It's not necessary to use dot y and dot z. You can do everything with dot x itself. Okay, so when your data is very large, then what you end up doing, which is going to be the typical case when you are running your simulations, is that you will fix this block size, which means the thread block size. And I'm going to, so these are just command line parameters to your a.out. This is the number of arguments. These are the actual arguments. I'm going to specify the problem size n using the argument number 1. And I'm going to allocate a vector, that is one-dimensional array of that size using CUDA malloc on the GPU and using malloc on the CPU. And then the number of blocks required, that is the number of buses required. So this is the bus size in terms of number of seats. The number of blocks required, number of buses required in our Mahabalipuram trip is going to be decided by C log n upon block size. And whatever is the number of blocks and block size that are specified as arguments in that launch configuration. And then I copy, I mean, from the GPU to the CPU, whatever I have computed on the D kernel, and I print it, right? Similar to our previous case. How does the GPU code look like? Well, it looks exactly similar to what we had earlier. This formula remains the same, and then vector of ID equal to ID. Okay. Any questions on this particular code? Okay. If you don't have any questions on this code, then I'm going to ask you some questions, right? So there are two issues in this code, right? And you have to find out what those two issues are. So please understand, look at the code carefully and find out those two issues. I'll give you a hint by specifying where the issues are. These are the two places where one is if condition for bound checking, very good, right? The way we did in one of our earlier programs, string length program, right? Hello world. And Soumya has found out the second problem, that the n blocks can be 0, float should be inside C. Go. So you got the answers, right? So this can go out of bounds, right? So think about it this way. Let's say my n is 2000. The value, the problem size is 2000. How many blocks will I require? So if I require 2 blocks of 1024 size. But as soon as I create 2 blocks of 1024 size, I have 2048 threads. If I have 2048 threads, then I'm going to do array out of bound access here, right? Because some of the 24 threads are going to do array out of bounds access. Right? So that is one problem. The second problem is I am doing integer division, n divided by block size. It should be a floating point division. So I need to fix that. So yeah, so this is one problem which we encounter quite often in the initial days, and therefore I thought that I'll make it explicit. So this you should always remember to do it in a proper way. Good. Thanks guys for these answers. Any questions on this so far? Okay. So yeah, this I'll leave you as homework exercise. So we need to read a lot of XY points, and then we want to compute the Euclidean distance between them, all the points across each pair using this formula, right? We would like to do that in parallel. And I would like you to think about in what ways you can parallelize this. And then finally, you want to also print the maximum distance. So please think about how you will be able to do offline. Okay, so just a brief note on various GPU languages. We have this CUDA, which originally was named as Compute Unified Device Language, but nowadays we just call it CUDA. It's proprietary, which means that it works only with NVIDIA GPUs. There are languages like OpenCL, called Open Computing Language, which is supposed to be universal, works across all computing devices or wherever the vendor supports it. So for example, it works also on CPU, also on NVIDIA GPU, also on AMD GPU, for example. Then there is OpenSEC, which is similar to OpenMP. Those of you who have programmed on parallel programming on CPU, these are called as pragma-based languages, right? So hash, pragma, OMP, parallel, for. In a similar manner, we have this OpenSEC, which is pragma-based. It's also supposed to work across various accelerators, which means that if you have NVIDIA GPU or FPGA or Intel GPU, then it is supposed to work across this. There are also some libraries and interfaces like Python to CUDA conversion, JavaScript to OpenCL, LLVM to PTX. LLVM is C intermediate code, intermediate representation. PTX is the intermediate representation for CUDA. Yeah, so this is just a brief note. Then there are two configurations of GPUs which I am showing. So this is called as a Pascal 100 GPU, and this is a Volta 100 GPU. The number of streaming multiprocessors, that is the actual multiprocessors which exist on these, might be a few tens. And the number of CUDA cores might be spread across these SMs, right? So the CUDA cores are grouped into these SMs. So 3584 divided by 56 will be the number of cores per SM. Then there is also tensor computation possible on Volta onwards. And then there are some other parameters possible. The amount of memory was little limited so far. It has been increasing. It has gone up to around 80 GB with Ampere and might increase further with the Grace Hopper architecture. Compute capability signifies what we were talking about as gen code or SM underscore some value. That is the streaming multiprocessor compute capability, which indicates for what GPU you want to generate code for. Mostly your code should work independent of this, except when we go further into specific advanced constructs. The peak FP64 throughput can be large compared to a CPU, which can be around, let's say, 3 teraflop. So this can be really fascinating for some parallel processing. Okay, let's take one example of matrix query. So how do matrix query? Matrix querying is a special form of matrix computation, which is quite a regular operation in many of our applications. So on the CPU, the way we do it is using a 3-nested for loop, triply nested for loop, where there is a matrix and I'm going to compute a result, which is the square, and then there is some matrix size specified. In our example, I'm going to take 64 as the size. So I goes from 0 to matrix size, J goes from that, K goes to that, and then the result of I into matrix size plus J, right? So I plus J is in terms of plus equal to IK into Kj, right? We are assuming that the result is initialized to 0. Right? That is where that plus equal to will come into picture. Alternatively, you can initialize it here. Okay, so this is our typical matrix multiplication code, which in this case becomes matrix squaring code. This we would like to parallelize, right? So one of the ways in which I can parallelize this is take the outermost loop and parallelize it, which means that I create a kernel which will have j and k loops inside its body, and the number of threads with which I launch the kernel is going to be equal to matrix size. That is the number of iterations of the I loop. Right? That is one way in which we can parallelize. The other way to parallelize is I parallelize both these loops together. Third way to parallelize it, I parallelize all these three loops. That is, I launch a kernel with matrix size into matrix size into matrix size number of threads. Right? So there are different ways in which this gets done. But currently the code I'm showing is only on the CPU, and when I try to run it on one of my CPUs, it takes 1.527 milliseconds for matrix size equal to 64. Okay. And we expect that when we try to parallelize it, we get some benefit. So let's parallelize it on the GPU. So the first version is that it's going to call the square kernel with 1, n as a parameter. Since n is 64, it fits into the bus size. And I'm going to call it with the matrix input, result, output, and size of the input. How does the code look like? Well, I compute the unique ID per thread, and then the rest of the code is exactly similar to what it was on the CPU. There is a J loop, there is a K loop. I loop is gone because that is now a parallel processing happening with n threads, where n is the matrix size, which is the I loop. And the code remains the same, result just that instead of I am going to use ID, which is computed as a unique number using thread IDX and block IDX. Okay, so result of IJ plus equal to matrix of IK into matrix of KJ, right? So that is what we would like to utilize. Any questions on this parallelized code? Okay, so when I try to run this code on my GPU, I get 6.39 milliseconds as the code, and the CPU was actually faster. Right? This means that not always the parallelization is going to help us. Right? Sometimes we might, some codes are sequential, and doing it on the CPU is better. And sometimes the parallelization might not be enough to compete with the CPU processing, right? So we'll probably improve the code further, right? So as we were discussing, let's try to parallelize the second loop also. That is our version 2, in which case I'm going to launch it with multiple thread blocks. Earlier it was only one thread block. So n cross n number of threads, and now the kernel is going to have only one loop, only the K loop. I and J loops are going to be essentially converted to block IDX and thread IDX. Okay. So the signature remains the same. ID is computed uniquely. This code remains the same, just that now it's going to use this I and J plus equal to matrix of IK and KJ. But how are we finding out I and J values? One way to find out is just say that II is block IDX and JJ is thread IDX.x. That is one way. Alternatively, you can do certain computation like this, the division and mod, and that is going to give you the same values. So either way should be all right. And when I try to run this better parallelized version, I start getting some benefits compared to what it was on the CPU. Right? So this is just to indicate that there are multiple ways in which you can parallelize, and you might have to do multiple iterations to ensure that you get benefits. One thing that you can try is, can I interchange I and J, whether you get the same value, whether you get any performance benefit. And the second one is, can I parallelize K loop and what happens in that? Any questions on that code, matrix squaring code? Okay. So the GPU computation hierarchy, whatever we have studied so far, let's recap that. At the lowest level is thread, and what I'm showing here are the values, typical values, right? So anyway, it's a one thread. Multiple groups of threads. So we said that there is a thread block also, but between thread and thread block, there is something called as a warp, right? Which will we'll study soon. So the warp is a group of 32 threads. It's a fixed number, 32. All these threads execute in something called as a single instruction multiple data, or a SIMD fashion. What that means is that all the threads execute exactly the same instruction, just that they might be operating on different data items. All of them will execute add instruction, all of them will execute move instruction, all of them will execute a mult instruction, right? So that is called as a warp. Okay. Multiple warps are grouped into a thread block. Typical size or maximum size of a thread block is 1024 threads. Multiple thread blocks get assigned to a streaming multiprocessor, which is the hardware part of the GPU, which might be actually running tens of thousands of threads at any point in time in a time multiplexed fashion. And multiple such streaming multiprocessors are part of an GPU. And a GPU is capable of running even millions of threads at a time in a time multiplex manner, right? So at a time, only the number of core many threads are going to be parallel. Okay, so this is a computation hierarchy. Sandeep says, is each warp is SIMT or SIMD? Can you tell the difference? Yeah, it is SIMD, so to say, as far as warp is concerned, in the sense that they are actually operating at one instruction, but the thread per se is going to execute different warps and different times, and therefore it is called as a SIMT, single instruction multiple thread execution. This is a nomenclature from CUDA. It's not a very standard nomenclature, but different warps can execute different instructions at any point in time, but they all are executing the same code. Therefore, this is called as a SIMD as the name. But the parallel programming technology, parallel programming nomenclature has these four terms, right? SISD, SIMD, MISD, and MIMD. Right? So these are the four forms where SIMD is the single instruction multiple data format, which gets used in warp. Sandeep says SIMT across warp SIMD, the opposite, Sandeep. Single warp SIMD and across warp SIMT.
In earlier example, the N and M, so basically the second index is basically number of blocks, 1024, is it?
No, 1024 is the number of threads within a thread. That is our bus size. So that is the second parameter. The first parameter is the number of buses, the number of thread blocks.
Number of, that is basically the first line, the GPU that you are told, the number of buses, is it?
The number of buses, yes, that's correct.
Sir,
Yeah.
sir, if you consider a single warp, so all the 32 threads will be executing the same instruction at the same point, right? So
Yes.
then why can't we say it as single instruction multiple thread within a warp?
Well, I mean, it is so thread in case of SIMT, the thread essentially means the code that is getting executed for each thread, right? So that code is similar across all the threads. Yes, so SIMD is also SIMT, but SIMT is not SIMD, right? Because different warps can execute the code at different times, right? So it is more specialized version of SIMT, so to say. Right? Anyway, SIMT is a late nomenclature which is specific to NVIDIA CUDA. So don't take it as a very formal meaning, but yes, yes, you are right that within a warp also they are executing the same instruction. Just that is more specialized than saying that they execute the same code. Yeah, Vinod, go ahead.
Sir, in case of if-else conditions, so will it be SIMD? Because
correct, right? So what Binong is saying is that can I have some if condition which is going to cause some issues with this SIMD, where if I say that if thread idx.x is less than 10, execute the if block, otherwise execute some other code. In that case, is there going to be a problem, right? So that is our next topic, which we'll try to cover as much as possible in next 10 minutes or so, right? So what is a warp? Warp you could view as our Ravan, right? So all these different heads, right, can watch 10 movies in parallel and 10 different movies in parallel. But if Ravana decides that, or different threads decide that some heads want to go to the school, whereas some threads want to go to a theater. That might not be possible, right? So they all have to go together, right? So that is our SIMD execution. They have to execute the same instruction, but they can keep operating on different data items. Right? SIMD is single instruction, multiple data, and they all need to be fully synchronized, and this needs to be qualified with what Binong is suggesting. So let's get into that part, right? There is one misconception which says that all the GPU threads, all the millions of GPU threads, they must be executing in lockstep fashion. That is not true. Only the 32 threads of a warp need to be executing in lockstep fashion. That is, lockstep is like an army. They are moving together. So let's understand that with the conditional part that Binong was suggesting. So if I say that all the odd numbered threads should execute some code like this, and all the even numbered threads should execute some code like this, how does that happen? Right? So I'm going to pictorially depict that. So I'm going to mark these as S0, S1, S2, S3 as instructions. And the gray box is going to decide the NOP. If I say that the time axis is along the y-axis and the warp size is 8 in this case, but the same applies to 32, then all of them are going to finish execution of S0. All the warp threads, all the 8 warp threads or 32 warp threads are going to finish the execution of S0 together. Okay. Then only the next part is going to be taken for execution. This is executed only by the odd numbered threads, and the even numbered threads are masked out. Masked out meaning they are not executing any execution. They are not executing any instruction. So SIMD comes up with this small catch that the threads might not be executing any instruction, right? Which means that the warp threads are either executing the same instruction, or some of them might be not executing any instruction, which I'm marking as no. After they are done with S1's execution, the other threads, the even numbered threads, start executing S2, and the odd numbered threads now execute no. Right? After they both are done, then S3 is executed by all of them together. Okay, so this is the meaning of the lockstep processing. Just that they are going to diverge now whenever there is an if condition. So this divergence is called as a thread divergence or warp divergence, which actually is going to increase the number of sequential steps from 1 to 2, because you need to execute if block and else block separate, and therefore that is going to reduce parallels. Okay. So this thread divergence is not good from the performance perspective, and therefore usually you will see this statement that you should not have too many if statements in your CUDA program, right? Because that is going to add sequentiality. But that is not completely true. It's applicable only to the warp threads, and there is something more, right? So for example, okay, by the way, before this, are there any questions on this?
So one branch is getting executed, the other threads are doing some no op operation, or like what are other threads doing?
They don't execute because they are disabled from execution. So the correct term is they are masked out, which means that they are disabled from execution. They are not really executing any instruction, not even no.
Okay, and at the end of both the branches, they are synchronizing explicitly, or like what will happen?
Yeah, so they are always synchronized in the sense that every instruction they need to go in lockstep fashion as an army's first row, right? They all need to be in sync. So at the end of the branch, they automatically, since they have to execute the same instruction, they are going to get synchronized automatically. Sandeep says, what is the difference between warp divergence and thread divergence? There is no difference. These are just two terms for the same thing. Okay, so let's take one example, right? So does this code diverge? Can you think about it and tell me? Any suggestions? Yes, for more ID, more iterations. Yes, Chinmay, Devansh, Mitesh. Yes, ID may be different. Sandeep says yes because each thread does ID iterations. Yes. So the value of ID itself is different, 0, 1, 2, 3, 4, like that. And therefore the number of iterations of this loop, although exactly the same code is getting executed, the number of dynamic iterations is going to be different for different threads. And therefore there is divergence for this code. Right? I'll skip this second example. So since thread divergence makes execution sequential, conditions are considered to be evil in the kernel codes. That is not totally true. That's not a precise statement. Right? For example, if I say vector size less than n, then execute s1 else s2. Yes, there is divergence, but that's not really going to affect us because my problem size itself is n. So I don't want the other threads to really do anything useful. Right? So it's possible that I might actually get a fully without any thread divergence because all the threads are executing s1, right? And nobody is executing s2 because my problem size is limited, right? So therefore there is no thread divergence. But then what we said is maybe the conditions which evaluate to different truth values. So some threads execute it with this condition being true, whereas some threads get this condition being false. That might be a problem. That is also not a problem. For example, if I have a code like this, yes, the different threads might execute, for example, if thread ID 0 will execute S2, whereas thread ID 32 will execute S1. But there is no thread divergence because 0 and 32 are in two different warps. The thread divergence is applicable only within a warp, not across. And therefore, this also does not lead to thread divergence. Okay. So the takeaway is that the conditions per se are not bad. They evaluating to different truth values, that is true or false, is also not particularly bad. They evaluating to different truth values for within a warp is the actual problem. Right? So as long as you ensure that all the threads within a 32 threaded warp, they evaluate to the same condition, then there is no thread divergence in your code, right? Which doesn't always happen, but that is the main point here. Okay, so this I leave you as a homework exercise. Some homework exercises here and marked here. So I kind of will stop here and we'll take up any questions that you may have.
Sir, can you please explain the for loops, right? Thread divergence. Use of these response.
Sorry, Shikhar, I was not able to hear your statement.
So yeah, can you please explain the for loop example where the upper limit was ID?
No, I'm not able to hear it properly. Maybe can somebody hear Shikhar correctly? Maybe you can reiterate what Shikhar says. Or Shikhar, if it is okay, will it be possible for you to type out the code? Please explain the loop example once again. Sure. So in this case, this loop is getting executed by different threads for different number of iterations. So 0 thread executes it 0 number of times. One thread ID I executes it I number of times, and therefore different threads execute it for different number of iterations, and therefore we are saying that there is thread divergence. So when thread number 10 is executing 10th iteration, at that time 0 to 9 are executing nothing. Right? So that is what we are calling as no op. That is what we are calling as thread divergence. Although technically that is not really thread divergence because the other threads don't have any other work to do. There is no else part to be done. Right? But if there would have been, then it would have led to a thread divergence. Sure. Any other concerns, questions on anything we have seen so far? So I'm leaving some slides for as a backup. Those, in case you do some more computation with CUDA, you might find those helpful. But as of now, whatever we have discussed, that is going to be sufficient. Mitesh has given some answer to, I think, this part. X equals y and then y plus y and then z. I see. Okay, let's see. So if this is true, x equals z. I see. That seems to be true. Anybody sees any issues with Mitesh's answer? I find this to be correct. So if x equals y, then x gets the value of no. Oh, I see. No, I think we need to also, okay. So if x equals y, I'll have to think about this. I'm not sure, Mitesh. Maybe you are correct, but I'll have to think about this. 1 and value 1 plus 0 and value 2. Oh, so you are saying x equals z in the second condition, right? Not x equals y. Okay, sure. That should be possible, I think. Sandeep says x equals y and val 2 plus x equals y and val 1. Maybe the opposite. Sandeep. X equals y and no, how come both the conditions x equals z and val 2 plus x equals y and val 1? It should be. Or actually, yeah. Or the negation of x equals y for val 2. All right, but are there any other concerns, any questions?
So I have a question regarding the trade divergence.
Yeah, go ahead.
So, sir, trade divergence just affects the parallelism, or it can give a wrong answer also? Maybe it's a very naive question.
Okay, so why do you think that it will give a wrong answer?
So like if it takes defined branches, so is it possible that for the particular instance of the program, it went to a wrong branch? Like maybe I have some difficulty in understanding this.
That will usually not happen because see what will happen is that you are going to write the program. So
Right.
as far as the condition is written, it could be thread ID dependent or it could be data of thread ID dependent. For example, if data of thread ID x.x is greater than 0, then only process this. Right? This could be one such statement. In which case there could be a data dependent thread divergence. As long as that code is written correctly, there is no problem because of specifically thread divergence. But since you have mentioned this, I'll mention one small piece which is not in our control. That if and else statements, let's say there is S1 in if and S2 in else, it's not guaranteed that S1 will execute first or S2 will execute. This is left to the scheduler. And if there is a dependence across these statements, even across, for example, the same thread is not going to execute S1 and S2, but different threads might execute, right? So if there is some data being written by S1, which is being read by S2 or vice versa, then the ordering in which this gets done might affect the final output. So that small catch might occur, but otherwise, if our code is written sequentially correctly, it will work in parallel also. I mean, warp divergence will not cause any issue because of that.
Okay.
Chinmay says, are there any hardware consequences for thread divergence in terms of heat or power requirements? I'm not aware of this, but likely that there might be, in the sense that since some threads might get masked out, maybe the power requirement is going to be low for a divergent branch compared to non-divergent code. Even the codes that we have written, we might end up doing more work. So the energy requirement that we have might be slightly more compared to an if-else statement. That's also possible. But yeah, people have not really worried about that so much in the literature, which probably means that the heat and power requirements for these computations might not be substantial or significant. The heat and power requirements because of, let's say, memory access or synchronization might be much larger.
So also the thread divergence, does it matter which branch of the condition is executed first or second?
In general, it should not. In general, it should not. But if I have a code like that, where I write to X in the if branch and read from X in the else branch, then I might see different values depending upon how the code is, and maybe have read from Y in the if and write to Y in the else. Then there might be a cyclic dependence. So the ordering might matter.
Then
So
that can lead to incorrect results, right?
Well, the code itself might be originally incorrect if we are writing it like this, because this is not a typical program. This is not how you will write the code. So typically that doesn't happen. This is more like an extreme case, more as a toy example. But yes, it can change the output depending upon the ordering of if and else. So Shikhar has given one another piece of code, x XOR y and x equals y, or x equal, oh, x equal to y and x equal to, yeah, that might no, I don't think so, Shikhar, because the second part of ampersand is going to be 0 or 1, and the first part of ampersand is also going to be 0 or 1. So we need to get the value rather than only the binary. So although x equal to and x equal to z is ensuring that you get the value. Oh, but that is getting assigned. I see. Oh, that is getting assigned to x. I see. No, I don't think so. I don't think this will work, because this will assign the value to x all the time, right? So x equal to, I think this will not work out. So as long as y value is non-zero, x equal to y will assign non-zero value, which will evaluate to true, and x XOR y is probably okay, but I think this will not give the correct answer. What Sandeep has also mentioned, that seems to be okay. Yeah, thanks Shikhar for confirming. Yeah, Sandeep, y plus z minus x should work out. Yes. All right, so we'll stop here. If there are any questions, please feel free to mail me or post it on the group, and one of us will reply. Your assignment is already out, so spend some time after lunch working on the assignment. Whatever we have studied, you might have to go through it a little bit and do that assignment. But hopefully, but definitely it is doable, right? And definitely doable in a few hours. So, and then submit it at the form that has been shared by Ashwin. Okay, are there any final questions?
So regarding assignment, I just had a small question. So I was trying to do it in Google Colab. So when I was trying to do it using the percentage CU tag, and when I was trying to read input using C, it is not letting us to read any inputs. It is just printing that take input, but it is not giving any box for taking the user input.
That's right. So you'll have to use the input redirection. I'll just write it in the chat. A.out taken input from file.txt. This is the kind of syntax that you might have to give, where you'll have to create file.txt in the same directory. So the input, I mean, the Google Colab is not interactive, and therefore directly it will not work. So you can have scanf there, but you'll have to put it, take the input from file.txt. So instead of typing it, type it inside file.txt, whatever input you want to give, And yeah, as Sandeep has also suggested, you'll have to redirect the output either to output.txt or it will print it on the screen.
Okay, sir. Thank you, sir.
Yeah. And feel free to discuss this on the group also in case you face any other issues, because some of you might have answers to this, and feel free to answer also, right? So your evaluations are independent of each other. So please help each other also in case TAs or us take time in answering. Okay, we all need to work together. All right, so I'm going to stop here. We'll meet tomorrow at 9 o'clock to discuss the assignment. So first 30 minutes, we are going to discuss the assignment. And at 9:30, we'll start wondering about the memory aspect on the GPU. Okay. See you guys. Bye.